It's my great pleasure to introduce James Sellers from Penn State University today. He just told me that he got Fulbright to go to Austria next week, I guess.
Yeah.
Next week?
Yeah, for the semester there. Yeah, it starts in March.
So today he's going to speak about unique path partitions, characterization, and congruence. Thank you very much.
Thanks. Thank you very much, Delaram. So, thank you all for being here. Let's begin. So let's do the first things first. Thanks to Delaram for her invitation. We met at the joint meetings 6 weeks ago, I guess, or something like this. And lo and behold, a week or two later, I was invited to be here. And the first thing I think I told her was, I'm not in algebra. And I tried to talk her out of it very quickly. And I was unsuccessful in doing that.
She's stubborn.
Yeah, so thank you. I appreciate it. It's a pleasure to be here. I'm very pleased to be here. I will try to make it clear where my expertise lies and where it does not. So there will be parts of this talk that are really stolen from other people. And in fact, it is an honor to be here. And thanks to each of you for being here. I appreciate that. This is joint work with two people whose names you might actually know better than mine. Christine Bessenrodt, who's in Germany, and Jorn Olsson, who's in Denmark. And I'll just very quickly tell you a bit of a timeline so that you get a sense of context. Last summer, I was sort of trolling the internet for papers and ideas, just sitting out on my back deck, enjoying my laptop in the beautiful weather, and just happened to start looking at some work of Jorn's on his website, and I ran across a preprint of something they had done on these things called unique path partitions. So really, I joined this game late because they had already written, in essence, a brief preprint on characterizing these things called unique path partitions, and they came at these from a representation theoretic point of view, which is where they live most of the time. It's not where I live most of the time from a research perspective, but it's where they live. And so really this starts from their motivation. And it's a fabulous work that they did, a result that I'll show you later in the talk. And then from there, I wrote to them and said, you know, I think we could do more. I think you could do more, I initially said. And then eventually it became we instead of the two of them. And so that's the genesis of this work. It really started with Jorn by himself. Christine joined later, I think. And then I joined after that. So it's really a three-step process that we went through. So my goals for the talk include the following. First, I want to define these unique path partitions and share some motivation for why we consider them. And I want to point out that the key word in this bullet point is briefly. The motivation is not my motivation. I really want to eventually get to the partitions themselves because I'm a partition theorist. And I want to count them. And I want, for any weight n, I want to be able to know how many there are. And then I would like to get to arithmetic properties of this function that counts them and so on. I also want to show you some examples of partitions which are or are not unique path partitions. We'll actually spend several minutes walking through how you see whether a partition that's given to you, its Ferrer's graph, really makes that partition either a unique path partition or not. We'll look at the characterization then of these things, and I'm going to discuss links between these things, unique path partitions, and binary partitions. So I've spent a lot of my career looking at binary partitions, which are partitions where the only parts you're allowed to use are powers of 2. That's where the binary comes from. So you're allowed 1s, 2s, 4s, 8s, 16s, and so on. There's a very, very tight connection, which becomes very clear. And then I want to share a number of arithmetic properties. So going back a la Ramanujan to congruences which are satisfied by this function that counts these things. That's where I live. And so that's where I want to get to. And that'll end the talk. Okay? So let me give you the motivation. So the Murnaghan-Nakayama formula gives a combinatorial rule for computing the value of the irreducible character of Sn labeled by the partition lambda on the conjugacy class labeled by the partition mu. I'm going to say nothing else about that paragraph. Okay, that is Bessenrodt and Olsson through and through. But that's really the starting point for looking at these partitions. And this value that was referred to in the previous paragraph is the weighted sum over the mu paths in lambda. So mu and lambda are going to be two different partitions, basically. And this weight that you're going to see is a sign that corresponds to the sum of the leg lengths of the rim hooks removed along the path. So we're going to be looking at taking one partition and using it to denote the leg lengths of a hook, of hooks. And we're going to rip out of the other partition the hooks that are of those leg lengths. That's basically what's going to be happening. Okay? So if mu, let's say, is A1 up to AK, and I'm going to be writing these with the largest part on the left and then going in non-increasing order, which is not uncommon. And if lambda is also another partition, then a mu path in lambda is going to be a sequence of partitions labeled lambda naught up to lambda k, where for any I, the partition lambda I is obtained by removing one AI hook from lambda I minus 1. So I'm just going to be removing one hook at a time. I'll show you examples in a second. And we're going to say that mu is a unique path partition for lambda, or an up partition for lambda, if the number of mu paths in lambda is at most 1. And that at most is very important. Okay, there may be times when you actually can't find a mu path in lambda. I'll show you an example in a minute. Okay? And then we're going to say that mu is a UP partition of n itself if it's a UP partition for all of the partitions that have weight n. So it's pretty special actually to be a UP partition. You have to be a unique path partition for every one of the partitions of n in question. Okay? So that's the idea. I want to be able to count those eventually. And so now let's look at some examples. So I don't want to bore you, but I find this the kind of topic where if you don't see some examples, you're not really going to understand what's happening. So let's just walk through a few. So I'm going to start with one which is probably a bad one. I actually care about teaching a lot, and I'm not sure that starting with the same mu and lambda is the right way to go. But let's start with that anyway. So mu and lambda here are 3, 2, 1. And now what do I want to do? I want to go through this process of finding a mu path in lambda. Okay? So I'm going to start with lambda. 3, 2, 1. I think probably most of you in the room, there's 3 dots here. That corresponds to that 3. There's 2 dots and 1 dot. So that's the 3, 2, 1. This is the Ferrer's graph of 3, 2, 1. Okay? And now what I want to do is I want to remove a 3 hook from this guy. So I'm going to use mu now to be my hook lengths. And I don't know if you guys can see that very well, but this little dot became red. Okay, so I'm going to remove the 3 hook that's there. And it's a 3 hook because I have 1, 2, 3 dots, right? That thing has length 3. All right, everybody okay?
So it's number of horizontal and vertically adjacent.
Correct.
dots?
Yeah, I'm sorry. Yeah, I shouldn't assume too much. So a hook length is going to be the node itself will be 1 plus all of the nodes to the right plus all of the nodes below. Okay? So I think the representation theorists like to call this the arm, and they like to call this the leg. Okay? If Rishi Nath was here, he would have told us that. Okay? But he has skipped out on this talk, and I just want to say, with the camera rolling, I'm very sad that he's not here today. Okay? And no, we do not have to edit that out. Now, so that's a 3 hook. So I'm going to remove it. Those 3
And you
red
could
nodes.
just as well taken the other 3 hook.
Oh, don't say that yet, Mel. It's a very linear talk. You can't say that yet. But you're right. You're exactly right. Which means, Mel, that this is going to end up being not an up partition. That's right. But let's walk through it. So I remove it. I have this thing. So I've started this sequence, right? Now what I have is a 1, 1, 1 partition. And now I need to remove a 2 hook. That's the next part in mu. There is, by the way, only 1 2 hook here, and it's going to come off of that node right there. There is no horizontal piece, but that's okay. It's still a 2 hook. I remove it. Now I'm left with that 1 dot, so now I'm down to just the partition 1. I need to remove a 1 hook. Well, there is only one way to do that. It's just sitting there in front of us. And so this is the mu path in Lambda that we just created. Okay? And now, since Mel is here, we can now do the second way of doing this, right? Which is to use that node right there. So there's another 3 hook hiding right here. And as I walk through that, now that removal gives me this. And the problem now is that I have a different mu path, right? So this guy will now be a 2 hook that I can remove. Remove it. And now I'm done. And there's another mu path, right? So I now have 2 mu paths that are distinct inside Lambda. And that means that 321 is not a UP partition of 321. Okay? That's easy. Now let's keep going. So, oh, and so I should point out then that once you're not a UP partition for one of the guys that's weight 6, then you're obviously not a UP partition of 6. Okay? Because that's where I want to eventually get. I want to be able to know how many UP partitions there are of 6. Okay? Or any other number you give me. Now, this example now tells me a way to build lots of partitions that are not UP partitions. So let me show you one example of how I might do that. So for example, I could tack on a larger part now and imagine that it is not a UP partition of 10. 4 plus 3 plus 2 plus 1 is 10. How? Well, go back to the Lambda that we had, 321, and just tack on 4 more dots or add 4 to the largest part. And what's going to happen then is that this will be your Lambda start. And now you need to remove a 4 hook. And if you stare at that long enough, you realize that there's actually only one 4 hook. And it's at this dot right here. Okay? And once I have that and I remove that 4 hook, I start my path and now I'm at 321. And of course, once I'm at 321, I know that what's left is not going to work well. So now I can build 2 mu paths for this guy, which are just cobbled off of the 2 mu paths of 321 that we had earlier. Are you with me? So now I know that 4321 is not an up partition of 721, and therefore it's not an up partition of 10. Okay, so there are going to be a lot of partitions which will not be unique path partitions. All right? And to be honest with you, it makes you wonder if there are going to be any up partitions at all. So this talk would not be very exciting if there were no up partitions of a number n. I might be done by now, huh? But I won't be. There's more to do.
You still have to prove it.
I still have to prove it, and I will give you that, at least a sketch. I'll give you a sketch of how to count these things. There are lots of them. But let me show you an example. Let's do a small example. So let's convince ourselves that mu, which is just 3, 2, is an up partition of 5. So now what does that mean? It means I have to check that it's an up partition for every partition of 5. There are 7 partitions of 5. So I'm going to do this quickly, but I'm just going to convince us that it actually works. Okay, so here we go. The partition 5 is a partition of 5, right? And there's only one way to build a 3 hook and remove it. It's going to be there. Once I remove that, I'm going to have that 2 hook. I remove it. There was only one way to do that, and so that was good. So far, so good. Okay, so we have a unique 3-2 path out of that partition. Now 4-1. Well, there's only one 3 hook there, and it's right there. And I can remove that, and then there's only one 2 hook left on the screen. I can remove that, so I'm good. 3-2. So this one gets a little more complicated, but if you stare at it long enough, that's the only 3 hook that's there. Then there's a 2 hook. You remove it, you're good. Now 3-1-1, and this is why I wanted to show this example. There is no 3 hook here. All right, it's missing. So you pause for just a moment, and then you say, oh, that's okay. The definition said at most one 3-2 path through this thing. Well, there are no 3-2 paths through this thing, so by default, I'm okay. I just keep moving. There's no problem at all. And I go to the next partition of 5, which is 2-2-1. And now, if you think about it for just a second, I think we've looked at all of the conjugates of the partitions I'm about to show you. So this is the conjugate partition of the partition 3-2, right? By conjugate, I mean I've reflected across the diagonal. So if I were to take this and flip it over the diagonal, I would just have the partition 3-2, and we've already shown that has a unique path, a unique 3-2 path through it. So this is also going to have a unique 3-2 path. So that one's done. We've already seen this guy as well, except we saw it when we were turning our head sideways. When we looked at the conjugate partition, it's good. And this one only has one 3-2 path as well. we're done. So 5 has at least one up partition, namely the partition 3, 2. Any questions on that? I just want to make sure that's clear as to what I just did.
So
Question?
just so I understand the background. So this type of partition problem arose from the algebraists and wasn't looked at previously, in sort of partition theory.
That's my understanding. That's exactly right. Yeah. So these are very, as you can imagine, are very specialized partitions. These ones that have at most one path like this. Obviously, you could think about maybe partitions where you have at most k paths instead of at most one path. I think it's going to get very messy very quickly to try to count, to try to enumerate those. But you can certainly try to push that that limit on how many paths you could have. But yeah, you're right, Mel. This started from the algebraic side, from the representation theory side. Anything else? Yeah.
There was a book in the late 70s, I think, by Shimon Eben.
Mm-hmm.
It was computational combinatorics or something of that sort, and that had some roots of the counting of different partitions in there. So it might be a good idea to go back. It was only counting partitions, didn't bring this in, but in the way of counting, there might be implicitly some of the roots of these thoughts.
Okay, good. Maybe I'll ask you afterwards for the name again. Good. Anything else? Okay, let's keep going. So 3, 2 is an up partition of 5, and in fact, 3, 2 is one of the 4 up partitions of 5. There are actually 4 of them. No, I'm not going to make us see all 4 of them. But, oh, Chris is counting them for us right now, actually. 5 is one of them. 4, 1 is one of them. Oh, I'm sorry, I showed them all at once, Chris. I should have made you do it. 3, 1, 1 is also an up partition of 5. So there are actually 4 of them. And it would be really nice to understand where in the world they come from, right? I mean, I hope you realize that I do not want you to hand me a different number instead of 5, like 50, and try to count using what we just did, all of the up partitions of 50. It would be stupid, right? And slow. So there are lots of questions that now come up. One is, can we identify the up partitions much more efficiently than the way I just demonstrated? Okay, that's a good question. One would be, is there a nice characterization of the up partitions of n? Is there a nice formula? I mean, just because you get a characterization doesn't mean you can actually write down either a formula for the number of up partitions or a recurrence or a generating function or anything along those lines. I'd like one of those. In fact, I get all of them. But I would like one of them so I could do something. And lastly, the question that I care about the most is, does this function u of n, which is going to count the number of up partitions of n, satisfy any nice arithmetic properties? So these are the questions we want to roll into now as we continue on in the talk. All right? Oh, and I know the answers. The answers are yes, 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 and yes. Okay? So just in case you were worried, yes. It'll all be positive as we keep moving. Okay.
So they're all decidable.
They're all, yes, they're all decidable. We've already decided them. Yeah, that's right. Okay. So let's look at these affirmative answers. And let's start by looking at the characterization. Now, I'm going to be honest with you. We're still in the bulk of the work that was done by Bessenrodt and Olsson. So I'm going to show you the primary ingredients for characterizing these things. I'm not going to give you the depth, the details of the proof so much. But I just want you to see that the pieces really are not very complicated. And once you see the right pieces, you can glue them together and everything is fine. Okay? So here's how we work through the characterization. There are just a handful of lemmas that I want to show you. First of all, this one says the following. If mu is a partition, A1 up to AK, and you know it's an up partition, and the last part, the smallest part, is a 2, then the same partition where you replace that 2 by a 1, 1 is also an up partition. Okay? So, Chris, you're shaking your head. Makes sense to you? Okay? And I think if you view the hooks, so I was removing traditional hooks as I was going through the example I did. The example was very small, so you didn't actually see hooks that were sort of embedded inside the Fourier's graph. If there had been some, when you do that removal, you have to then shove all of the dots that are still remaining up and to the left so that you get a new Fourier's graph that's legal. The other way to view hook removal is to look at what are known as the rim hooks. So you pick that node that you want to be the corner of the hook. It defines a farthest most to the right dot and a foot dot, if you will, right? Any hook has those things. And then what you do, instead of finding the L shape, you just run your way along the bottom rim of the Ferrer's graph, and that process actually gets you to the same Ferrer's graph. Okay? And so this idea of changing a 2 at the bottom of a Ferrer's diagram to just a 1, 1, I think it makes even better sense if you think about rim hooks rather than hooks. Okay? Does this make sense? So that's not the way you were thinking of it, Chris. You want to...
Well, if you're thinking, if you're removing, if the last thing is removing 2, you have to end up with either 2 like this or 2 like that. And
Okay.
we only wanted a way to remove 1 and then 1.
Okay. Okay. All right.
I like that.
Yeah? Okay, you ready? All right. So the proof actually comes from the definition, probably, and maybe Chris and I are both saying this, but for me, rim hooks actually make sense in that case, but that's okay. All right, that's one lemma. It's a pretty straightforward lemma. The second one is this. If you have an up partition, A1 up to AK, where the number of parts now is at least 2, then the removal of that largest part will still give you an up partition. Okay? So the proof here actually is by contrapositive, if you really want to know the truth. So the idea here is, instead of trying to prove the lemma as it is, you write the contrapositive, and if this smaller partition has 2 or more mu2 paths, then any partition of n obtained by adding an A1 hook is going to have 2 or more mu paths, and that's basically the proof. Okay, so really the way to write the lemma might be as it's contrapositive, but this is the positive way of writing it, okay, about when you are an up partition. Okay, so that's a second lemma. And a third lemma is actually the one that we used to an extent to prove that 4321 was not going to be an up partition earlier. It basically says this: you take a partition, any partition, all right, of n, and you also pick another number a, which is bigger than the full sum of all the parts of the partition you've chosen. Then this guy is going to be an up partition if and only if the partition you have where you add on this as an extra part is also an up partition. So this is a sort of, I don't know if you wanted to name the lemma, but it's basically the add on a humongous part lemma and you'll still get an up partition. And the idea, I think, there is if you've added on a new part which is so big and you want to start removing a large hook first, there's only going to be one way to find such a hook, and it's going to involve that largest part that you've added on. So this is a sort of mega part lemma. Okay, if you add on a really big one, then the original partition is up partition if and only if this new one is an up partition as well. Okay, I should point out that the previous lemma that I just showed you is half of this if and only if. So actually the proof here, you only need half of it. And then you can walk through. I'm not sure I really want to do this as we have it here, but basically the proof really is about that long. Okay, that's it. And you just walk through and you talk yourself through the idea of having 2 or more of these A hooks. So you start with this idea of having this really huge hook and then asking yourself what would have to happen if you wanted to remove that one hook. And it falls out. It's pretty quick. Now, believe it or not, that lemma motivates a definition, which is something called strongly decreasing, which says the following. If you start with a partition of n and you tack on one of these really large parts A, which is bigger than the weight n, we're going to say that that's called a partition which is strongly decreasing, or it's going to be an SD extension. So you can imagine these partitions now have this property that their partial sums of the parts, starting with the smallest part, have to satisfy certain inequalities, strict inequalities. Okay. So we're going to worry now about these things called SD extensions of rho. So mu is going to be a partition obtained from this partition rho by several of these SD extensions, just adding on huge parts, larger and larger and larger parts as you go. We're going to call those SD extensions. And if your starting point is just the empty partition, we're going to say mu is an SD partition. Okay? So this is the defining statement about SD partitions. Mu, which is this guy, is going to be an SD partition if and only if these partial sums all satisfy this strict inequality as you read. I guess in this case, well, you can read it left to right or right to left. It doesn't matter. But the point is that if this is the smallest part here, as you start reading this way, these parts have to be growing immense as you go. Okay? And that'll be important for us a little bit later. Now, just a quick side note, which is a very self-serving. It looks self-serving at the beginning. Okay? I want to make it clear that it's more than just self-serving. These guys that are defined in this way look a lot like some partitions that hit the literature just a few years ago, and were named by, actually, Neil Sloane primarily, of the Online Encyclopedia of Integer Sequences, but I had the privilege of writing a paper with Neil on these things, and we called them non-squashing partitions. And the non-squashing partitions have a definition that looks very much like these SD partitions. So here's the definition of SD partitions. Here's the definition of non-squashing partitions, and believe it or not, the only difference is that here, this is strict inequality, and this is greater than or equal to. That's it. And Neil and I had no reason to be looking at these, what we're calling now SD partitions. But it tells you that there's probably a strong connection between the two. And in particular, these non-squashing partitions about which Neil and I wrote bring up binary partitions, these partitions into powers of 2, very, very quickly. And so you imagine that these SD partitions are going to be linked very closely to binary partitions as well. Okay, and that actually is the case. Now, just to give you the classification of these up-partitions very quickly, here it is. You hand me a partition mu at lunch today, I can tell you whether it's an up-partition, it has to satisfy one of two things. Either it's an SD partition, so that the parts all grow, starting with the first one, the smallest one, you have to keep checking these partial sums as you go, and each new part that you add to the left has to be larger than the sum of the previous, or the following parts, I guess. Either you're one of those, or you're an SD extension of the partition 1, 1. So for example, can I use this black? Is this a picture? So as an example, really? Can I? No, I can't. Okay. Let's use that. Obviously, let's take something like this. This is not in an SD partition by its definition, because this one is not strictly bigger than this one. Okay, so this guy 311 is not one of these, but it is one of these second ones. Okay, so that's the only difference between those two bits. And so now if you think about it for a moment, it turns out that if we go back to 5...
Oh, that's it, those two.
Oh, say that again?
That's it.
That's it. Yeah, I'm sorry, Mel. I didn't do enough to dine. That's the characterization. And so now if you have all the partitions of the number in front of you, you simply need to check these partial sum statements, and either it has to hold forever as you read from right to left, that's what this says, or you're allowed a 1, 1, and then it has to hold after that. That's the whole characterization. Okay? So, here are the partitions of 5. We looked at this example earlier. Chris already told us the 4 partitions that were unique path partitions. They were the top 4. Those 4 that are in red now. Notice that the top 3 are SD partitions. I mean, I know that they're small, so it doesn't look very exciting, but they do satisfy the partial sum result. Okay? This guy, the bottom one, the 4th one, is not an SD partition, but it is an SD extension of 1, 1. Okay? And the other guys are no good. Right? This 2 is too small. Okay? Because 1 plus 2 is 3, so this needed to be at least 4 in order to be okay. This 1 is too small. Several of those 1s are too small. Okay? So this is the full characterization. That's it. Now, the problem is that it's nice, and by the way, I think it's safe to say that we've now reached the end of what Olsson and Bessenrodt had done when I read their work last summer. Okay? And my thinking was, boy, that's nice. I mean, what they just did is really nice. But if somebody walked up to me and said, okay, what are the UP partitions of 50? that characterization is not going to help me a whole lot. Okay, I mean, I'd rather be at lunch with you folks than trying to figure that out. Okay? Well, okay, with most of you. But that's going to take a long time, right? I mean, you're going to have to write down all the partitions of 50 or try to build them somehow from scratch. It's really going to take a lot of time. Okay? So the goal of enumerating these up partitions for a specific value of n I thought was still up in the air. Okay, and that's where we're going to go next. Okay, so I want to try to understand how to actually count them. So you walk up to me and say n is 50. I want to be able to say the number of them is this, okay, quickly. So let's talk about that for a second. And I'm going to do this from the perspective of generating functions because it's really I think the quickest way to start. So u of n for us is going to be the number of UP partitions of n. I'm going to define an SD sub t partition to be an SD extension of the partition T. So let me be clear on this. This is the partition that has one part and it's size T. Okay, so its Ferrer's graph is just one row of T dots. So this SD sub T partition is just going to start with a T. Okay, we'll start with a T here, and then whatever you want to build after that has to satisfy this SD extension issue. Okay, so there you go. And I'm going to say that the number of SD partitions is Sn, and the number of SD sub t partitions of n is S sub t of n. And what does that mean? It means I've taken all the partitions that are SD partitions, and I'm counting them, I'm putting them into sets based on what their smallest part is. That's basically what I've done here. Okay, so S of n is going to be S1 of n plus S2 of n plus S3 of n, dot, dot, dot. Okay. And remember, S of n is counting the first type of the partitions that were in the characterization. Okay? S of n is counting, sorry for doing this, these. All right? So I'm going to have actually most of the formula if I know S of n, believe it or not. Okay. So here we go. Now let's get a quick lemma. This is the last of the quick lemmas in the talk. If mu is a partition of T, then there's going to be a bijection between SD extensions of mu and SD sub T partitions obtained by replacing all the parts of mu by one part T. In other words, if you give me a partition mu, which has some weight n, and you ask me to count all the extensions starting with that as the partition, the first partition, then the number of those, not what they look like, but the number of them will be the same as if I had just squished mu into one part of big size, that same size, okay? So I can find a bijection between those two sets of partitions, okay? Good. What does that mean? That means that u of n then is just S of n plus S2 of n, because remember, the characterization said you can either do the extension starting with 0, starting with an empty partition, or you start with 1, 1 and extend from there. Well, 1, 1, the number of guys you can extend off of that is the same as the number you can extend if you just started with a 2. Okay, that's the idea. So now, all of a sudden, I have this cool formula for u of n, except I have no clue what these two things are. Okay, so let's keep going. Now I'm going to focus on this Sn. And here's a nice formula which helps tremendously. S of n, which is the number of SD partitions, starting with the empty partition, is just 2 S1 of n plus S2 of n. So here's the proof. This actually goes very quickly. So let lambda be an SDT partition, so that what that means is this guy is a T, and then everything else has to grow big as you read right to left. Okay? You can now map this lambda onto the same partition where you subtract 1 from this part and then add a 1 as a part. Okay, so it's basically the idea of taking that 2 and making it a 1, 1, except now you're taking that last part and ripping one of its little dots off and making a new partition. And that means you're going to get a bijection between a set of all SDT partitions of n with T at least 3 and the set of all SD1 partitions. Notice, this guy now is an SD1 partition because it's got a 1 at the end. And as long as this part was a 3 or more, this is okay to do. And you know that you're safe. The only problem would have been if T, this had been a 2. Okay? not sure it would even be a problem at that point, but anyway. That means S1 of n, because I have this nice mapping, this nice bijection, has to be the sum t greater than or equal to 3 of st, because of this thing here. But that, keep in mind, Sn was just the sum t goes from 1 up of st. So now it's not real hard to make this pop out then. Okay? Basically, Sn is going to be S1 plus S2 plus that sum. So it's S1 plus S2 plus S1, which means it's exactly this. Now, something really cool from an arithmetic perspective has now happened, although you folks may not realize it. But that's why I'm here today. So here we go. Ready? U of n is equal to this. I showed that to you on 2 slides ago. But I just showed you that S of n is this. So if I replace Sn by that much, that Sn will be changed, and this is this. What does that mean? It means for any n greater than or equal to 2, U of n will always be even. Now that doesn't sound very exciting to you, maybe, but if you're a congruence guy like me, I just proved that I have a partition function that's always even. That's cool. Okay, so I got a mod 2 result. Turns out there's more to say than that, but that's the first little piece about U of n. Okay? All right. Fun. By the way, there's even more that can be said about U of n. It turns out that the values of U of n, I'll say this in a minute, but I just want to give it to you now because I think it's a more natural thing to say. It turns out that the values of U of n, if you look at them in a tabular way, come in pairs. So that I think it's U of 2n is the same as U of 2n minus 1 or something like this. Okay? So not only are they all even, but it doesn't take a rocket scientist to print the first 100 of these once you know how to get the generating function, and you see the numbers actually show up in pairs. And so in a moment, we're actually going to say that we'll only look at U of 2n, because U of 2n minus 1, I think, is the same thing. Okay? All right. So that was fun, but I'd like to know more about U of n than just that it's even for all n greater than or equal to 2. And so now, let's look at this further by trying to understand this connection to binary partitions. So that's where we're going to go next. And this leads me now to a couple definitions. So now I want to connect to certain binary partitions. So let me just do this quickly. We're going to say that a binary partition is called restricted. So it's just going to be a RB partition, restricted binary partition, if the following holds. So all the parts have to be powers of 2. Okay? You're not allowed anything else but powers of 2. And the restrictedness is going to be this. If 2 to the I, let's say, is the largest part, then you must have at least one copy of every other power of 2 appearing in the partition. And you could have 17 copies for all I care of some of them. But the point is there can't be any gaps in the parts. Okay, so if 16 is your largest part, you must have an 8, a 4, a 2, and a 1 appear as well. Okay, that's what this restricted means. All right, so they're binary partitions without gaps. Obviously, there's a big gap between an 8 and a 4. I understand that. But in terms of the powers, if you will, there are no gaps in the powers. All right? And then RB sub t is going to be a restricted binary partition where the largest part occurs t times. And now you can imagine that SD sub t and RB sub t might need to be connected. Okay? And it turns out that they are. Wow. I even said that before it showed up on the screen. Here we go. Here's a theorem, which is very, very helpful. You'd think I practiced this morning, which I didn't, by the way. I had other things to do. It turns out there's a bijection between the set of SD sub t partitions of n and the set of restricted binary partitions where the largest part occurs exactly t times. And the bijection is easy to see, so I'm going to show it to you. Okay. So if you have an SD partition, and again, just a reminder, that means that these parts are growing really, really big as you read them from right to left, so that they satisfy that string of inequalities. That partition is uniquely determined by these numbers, which I'm calling DI, which is AI minus this sum. Okay? Remember, this has to be a positive number because AI is strictly bigger than this sum. Okay? So the D's are positive numbers. And if you stare at it long enough, you realize that the weight n, which is supposed to be the sum of these guys, is exactly this. It says D1 plus D2 times 2 plus D3 times 4 plus ... dk times 2 to the k minus 1. And that's the bijection. I mean, in essence, that's it. Because these numbers have to clearly define your SD partition, and each of these Ds is positive, not non-negative. They're positive, which means I now have a partition into powers of 2, and each part has to appear at least once. Okay, so I'm done. That's my proof that none of the parts are going to be missing when I look at the binary side of things. And that's it. Okay, so that's really the connection now between these guys and these guys. Now these guys, I have no clue. These SD sub t partitions, I have no clue how to write down a generating function. But I know exactly how to write down a generating function for these binary partitions.
When in your previous work, it was not restricted, it was just like...
That's right. In the previous work, it was binary. Although in the work with Sloane, it turned out that what you needed were not all binary partitions. You had to actually then, actually it was the following. The ones you kept were the binary partitions where, if 2 to the I was the largest part, then a 2 to the I minus 1 also had to appear, but you didn't care about the rest. So here what's happened is we're now caring about all the rest. We're forcing all the parts to appear at least once. Okay? All right. Well, that means that S of n in particular, the number of these partitions where you start at the empty partition and just grow them, has to equal the number of RB partitions. And folks, this is the generating function then for S of n. Now, if you play with generating functions, maybe that looks obvious to you right now, but I'm guessing some of you don't. Okay? So let me show you where this is coming from really quickly, and let me try not to break any more pens. So,
You didn't break any partition, did you?
yeah, that's true. Yeah. I think it went from 1 to 1, 1 is what it became. Yeah, that's right.
That's a possible take on it, right?
Maybe from 1 to 1/2 plus 1/2. Okay, so what's happening here? Well, if you're going to give yourself binary parts, one of the things you could do is just have 1s, okay, which is a 1 minus q to the 1 in the bottom. But if you know that you must have at least 1, 1, you're going to throw a q to the 1 on top to guarantee that. So this is guaranteeing at least 1, 1, and then everything else is just 1s. No problem. If you're going to give yourself 1s and 2s, that's what your denominator is going to look like. But now you need a 1 and a 2, at least 1 of each. So you're going to do that on the top to guarantee that a 1 has to show up and a 2 has to show up. And so that's going to be the second term. That would be the I equals 2 term over there. And the third term is just going to be a 1 minus q, a 1 minus q squared, a 1 minus q to the 4th, but you need to guarantee there's a 1 and a 2 and a 4. And once you write a few of those down, you realize that that's the general generating function. And now once you have that, you go to Maple or Mathematica or whatever, Maxima or whatever your favorite thing is, and just tell it series. And bingo, you can get all the coefficients you want. Did I not say the right one? Should I set a different program?
No,
You didn't
No,
mention
no.
singular, no?
singular.
So I can get tons of values of S of n. And by the way, think about this from one more perspective for just a second. Notice that if, let's say I wanted the first 1,000 values of S of n, okay, just 1,000 of them. Because these exponents are growing by these powers of 2 in a geometric sequence, if you think about it, if I just want the first 1,000 values, I only need j to be up to about 10. So to get the first 1,000 values only requires me to crush out 10 or 11 terms in this generating function. So this now gives me a really rapid growth in what I can calculate. And it's very, very satisfying. Now that's not U of n, it's just S of n. Go ahead.
Probably a trivial question.
No.
If you know these things. So these generating functions, I guess, are built to do what you just said. They calculate large values. But when you go to a generating function, you could throw in small numbers. Like you said, if you wanted up, let's say the first 1,000 of them.
Yeah.
You use the generating function and throw a small number in.
Yeah.
Figure out what happens.
Sure.
That's the purpose of these.
Well, that's one
generating
purpose. I mean,
functions, yeah.
it certainly plays a computational role. That's certainly clear. But the other reason to worry about the generating functions is this. once I know the generating function, that's going to give me basically the sum of the Sn q to the n, right? What if I wanted S of, let's say, 2n q to the n, or S of 4n q to the n, which is where the talk will end. I can dissect a generating function like this by doing a weighted sum where I replace, as an example, let's say I want S of 2n's generating function.
Right.
I can take this guy, I can add to it the same generating function with q replaced by negative q. If you think about it for just a minute as a power series, what does that do? Well, all of the odd powers of q will cancel each other because the negatives are going to survive. All of the even powers of q will show up twice, right? Because the negatives will be killed off. And so if I add those two pieces that I just mentioned and divide by 2, I will now have the generating function for S of 2n. I can then play the same game to get the generating function for S of 4n if I want. And actually, I could do S of any arithmetic sequence you want. Instead of q and negative q, I could have q, omega q, and omega squared q, where omega is a third root of unity. Do the correct weighted sum, I could get S of 3n if I really wanted.
Yeah, I mean, my issue was really, why are these generating functions needed, but thanks for the explanation.
Does that help a little bit?
Yeah.
Yeah, it then allows me to start understanding arithmetic properties of those arithmetic progressions.
Okay.
Yeah. And because these are powers of 2, one would assume that the roots of unity I want are probably going to be, the second, fourth, eighth, etc. Really nice things will happen there. Fifth roots of unity might not behave very nicely here if I start replacing q by fifth root of unity times q. I doubt that it's going to be clean.
Yeah.
All right? Yeah. Okay. This, by the way, is the generating function for st of q. It looks more grotesque, but it's actually, if you just write down a few terms like this, you'll see the thing popping out. And remember, u of n is s of n plus s2 of n. So if I take this creature for s, and this guy for S2, and add them, I'll have the generating function. I'll be done. Okay? Yes, I said that earlier. And so now I have a really easy way to build U of n. Okay. Let me get to the arithmetic properties. See, now, what have I done? I spent 45 minutes doing the part that you needed to see, but now this is the exciting part. So if you've fallen asleep, wake up now. This is the right part to be. Okay. All right. So I'm going to suppress all of the proof now, but let me just show you U of n. First of all, we know U of n is even. What else can be said? Oh, yes. So I said this earlier. U of 2n is U of 2n minus 1. And so actually, I only need to look at U of 2n, because I know U of 2n minus 1 is going to be the same. Easily proven. I could do that with generating functions, by the way. I could find the generating function for U of 2n, like we just described. I can find the generating function for U of 2n minus 1. Instead of adding the two pieces, I actually subtract them. And if you think about it, then the odd powers would have survived, right? And so if the generating functions are the same, then I'm done. Okay, cool. I could also just do it with recurrences or something along those lines. So now I want to focus on this thing, which is just U of 2n, and I'm going to divide it by 2 because I know all the values are even anyway. I'm going to look at W of n. Oh, I can't show you that yet. I hope you didn't read it too quickly. You're now going to do a little bit of mathematics with me. I made these bright. Yellow, there you are. Sorry to make this feel like a classroom. Can you pass those around so I don't have to...
You also get
Oh,
homework.
that's very good. Those are happy days.
Happy days.
All right. I now want you to do... These are values of U of n still, okay? So you're now going to tell me something. I want you to look at U of n. They're all even. But I want you to actually now look at the mod 4 instead of mod 2. I mean, they're all even. You can see that on the page. Look mod 4 for just a moment.
Oh.
Don't say anything, Chris. When you say "oh" like that, it scares me. And I'll give you a hint if you don't want to play this game too long. The numbers with boxes around them are very special. So you should see pretty quickly that a lot of these are divisible by 4. Right? We all know this rule that to check if a number is divisible by 4, you just look at the number that's the last 2 digits of the thing and see if that's divisible by 4. And if you do that, you see very quickly that almost all of these are divisible by 4. But if you look at the ones with the boxes around the ends, you see that those guys are only divisible by 2 and not by 4. And the boxes around the ends, those ends are 2, 4, 8, 16, 32, 64, 128. You don't need Neil Sloane's database. Don't tell him I said this. You don't need Neil Sloane's database to know 2, 4, 8, 16, 32, and so on are the squares, right? And therefore, you have a theorem, if you can prove it, which says U of n is congruent to 0 mod 4, or the same as Wn is even, obviously, exactly when n is not a power of 2. This is a cool result. And we've proven it very quickly. And that's exactly what's on your yellow page. Okay? So that's a nice result about U of n mod 4, which, again, Jorn and Christine didn't look at this kind of stuff. They weren't really interested in it. But for those of us interested in arithmetic properties, it was a really cool thing to see. And this now allows you to build as many Ramanujan-like congruences as you'd like for U of n mod 4. As long as I can now find arithmetic progressions, Ramanujan was interested in arithmetic progressions, as long as I find them so that I avoid powers of 2, I'll have congruences to write down. So, as an example, U of 2 to the jn plus 2 to the j minus 1 is always divisible by 4, which is the same as W being divisible by 2 in those same values. So that's just one example of a family of congruences that we can write down for U of n mod 4. And now let me just show you really quickly, this is the kind of thing we can write down for W mod 4, which is the same as U mod 8. And as you can see, it starts to get messy. I mean, even I now think this is messy. And you can imagine that if you wanted to get mod 16, for example, it's going to get so messy that it's time to just do something else, like go to lunch or something like that, okay? So I can write these down for moduli that are powers of 2, but after a while it's time to do something else. And so let me move to the something else and then we'll be done. So let me just share a few thoughts. First of all, there are lots of other functions hiding inside this paper that the three of us have written. In particular, we proved more things about this S of n, which had that nice restricted binary partitions generating function. So for example, we proved that S also comes in pairs, not just the U function, but the S function. And it turns out that lots of these facts then about S can go into the binary partitions life. And now let me just point out something I'm actually currently working on with a colleague, and that is the following. This generating function, and actually it was this generating function for S of n, has a very natural M-ary generalization. Okay? Namely, the 2 can be replaced by any m greater than or equal to 2. You know what to make these exponents here. This would be 1 plus m squared, for example. And this would be 1 m and m squared. I mean, you could play the same game and get the generating function. And it turns out that you can prove lots of results for the M-ary version of this partition function as well. He and I are in the midst of doing that right now. And my hope is that, well, when I wrote the slides, my hope was that there would be numerous congruences and so on that they would follow. My hope is now a reality. So we know they're there, and we've proven some of them, but we haven't proven the full family yet. And that's what we're in the midst of right now. And with that, I'm done. Thank you for your attention.
Are there any questions?
So, can you say anything about what was the original algebraic problem that gave rise to these things?
You know, I have to be
What are
really...
the words that appear in the other guy's papers? That...
Okay, so just give... Oh, actually, Mel, hold on. So that's the... I'll give you the full first slide. That's the original motivation. And I'm not kidding. That really is the original motivation. So you can play these games between lambda, labeled by this partition lambda on the conjugates class, labeled by mu. And what you're doing is trying to understand these mu paths in lambda. And what Jorn wanted to do was just look at those values of those partitions mu that where you had only one path. So he's really restricting down in a sort of microscopic way, if you will, at a very special set of partitions. That was the original motivation.
But it came from trying to understand a little bit more representations of the set.
Right. Yeah, Chris.
So these the SD partitions, they're defined by some characterization of size of parts. And I know there's another type of partition called a lecture hall partition.
Right.
It's related to some Coxeter group theory, other things. Are they related at all? Do you know about the?
So they are, well, obviously they're related in the sense that the parts are defined in essence by inequalities that are satisfied. I think the big difference between those two families, the lecture hall partitions and these things, is that in lecture hall partitions you're only really looking at two parts at a time as you look at the inequalities. Mm-hmm. Here I'm having to worry about all of these partial sums all the way across the partition. So lecture hall partitions, for the rest of you, basically if you have these parts, you would want, correct me if I'm wrong, Chris, something like A2 divided by A1 would need to be bigger than or smaller than A3 divided by A2, which would be bigger than.
So the proportions.
They're proportions, that's right, as fractions.
I think it's similar.
Something like that. And then there are lots of variants of that kind of issue. So that's very different from here where I'm having to find these partial sums all the way across.
So you said during lunch we can give you a number and you could tell us the number of SD partitions.
If it's
I have about 45 examples. I hope you don't mind.
I'm going to keep one of these very close to me today for lunch. I'll tell you what, you tell me an even one, and I'll tell you the corresponding previous one. How's that?
Deal.
Any other question? So let's thank James for his excellent talk. And you can